So I'm going to be speaking about joint work with Stan and Leah and Dimitri, who are all in the room. So my title is, in fact, I'm lying a bit to you because it looks like I'm really going to speak about pneumatic colloids, which are like suspensions of many small particles inside a pneumatic liquid crystal, when in fact I'm just going to be considering one particle. So you could almost forget about the word colloid, but the motivation is, of course, to be understanding more about the interactions between particles in a pneumatic colloid. Those pictures I stole from, I think, a review paper by Stark, where you see that when you put a particle inside a pneumatic liquid crystal, if you have some anchoring on the boundary of the particle, then you create defects. And those are the two pictures that people expect when you have radial anchoring. Either you create a point defect or you create a ring defect around the particle, and I will be focusing actually on that situation. So in some sense, this is really like the opposite question to what Giacomo was telling us before. He was really studying like more like what happens when you have many particles and you have a kind of homogenization. And here I'm just studying like what happens around one single particle with the optic of, the goal is to understand better something that could lead to an answer to Peter's question, actually, about interactions, forces, stresses between several particles. All right, so this is, we're going to be working with the Lambda energy that you have seen already many times this week. So just recall what it is. So you have this elastic energy. We'll be working within the one constant approximation. And you have this potential. Here I'm using some rescaling, so I just have one parameter left, which I call Xi, which effectively is a length scale here in this scaling. And Q, as always, is with values into these 3x3 symmetric traceless matrices, which represent the orientation of the molecules locally. And the Lambda potential, where you could think of this polynomial form that we saw before, what we will actually be using is that it has this physical symmetry, okay, frame indifference, and that it is minimized exactly at uniaxial Q tensors with a fixed eigenvalue, with a fixed scalar order parameter. So here we fixed it to 1, but I mean it could be anything else. Just this is a special choice of units if you want. So I call this set where it's minimized, I call it U star. U stands for uniaxial, and star for the fact that you're fixing the eigenvalue. Okay, this Xi, I will call it the pneumatic coherence legs, because as I told you, it's a length scale. And we've heard also before that when this length is very small, so you study the convergence, what happens when it goes to 0, then you take minimizers of this energy. So I will be very vague about boundary conditions, but when I say minimizers, it with respect to some boundary conditions. So it might be some strong anchoring, it might be there could be some surface energy. But what you can always say is that if you have a family of minimizers with bounded energy, then as Xi goes to 0, you have strong convergence in H1. This is a compactness result. And bounded energy happens, for instance, if you fix a strong anchoring condition that does not depend on Xi. And it converges strongly with something that obviously has to take values into this set, right? Because now you are enforcing an infinite strength here. So in the limit, what you see is really just a vector field n star. And still, you don't forget that you were minimizing this energy. N star still has to minimize this one constant Gaussian-Frank energy among configurations which have to be S2 valued. So this is what in mathematics we call harmonic maps. And we saw before in this week that they have defects. I mean, they're not that nice, even though the analysis is quite standard now of harmonic maps. Okay, so this is H1 convergence, which is nice. But when you speak about this H1 convergence, you don't really see the difference between defects and more regular parts. And in fact, what happens is that if you stay away from the defects, then this convergence is very good. Here I say convergence is smooth. I mean, it's basically uniform convergence of all derivatives as long as you stay away from the defects. And this you can find, for instance, in the paper by Majumdar and Zarnescu, and then Nguyen and Zarnescu. And what it tells you effectively is that as long as you stay away from the defect, your minimizers Q of this energy, they are in fact very well described by just this n star. So where do you actually need to use the Q is just near the defects, right? Away from them, this is a very good approximation this year, right? So you probably want to keep this in mind for the rest of the talk. And okay, so this was like for the general thing about the Lambda de Gene. And now let's talk a bit about pneumatic colloids. So, I mean, you already had a wonderful introduction about them by Giacomo, and I will be saying a lot less about them, actually. But what's the spirit? I mean, you introduce particles in your pneumatic host, and since they have some kind of anchoring at their surfaces, they modify the pneumatic alignment, right? And this can create topology, and then you're forced to have defects. And also, since they are modifying the alignment at long range, it creates long-range interactions. And I guess so those are like the interactions that were hidden, I guess, in Peter's question. And this is really one of the things you'd like to understand, because then you have we saw pictures earlier also, like self-assembly phenomena. I mean, many things, many interesting stuff can happen. What we would like to do is, of course, to understand those interactions. And okay, before saying that, maybe let me tell you what those pictures are. So remember, I told you that Q effectively is very well approximated by just this unit director. So here, those lines are just representing the direction of this unit director. So what you see is not Q, it's actually N, which is depicted here. And around the defects here or here, you would actually have to use Q. And you have to think that those are 3D pictures. So you want to rotate them around the vertical axis, right? Yeah, so those long-range interactions. So one theory that seems to be, before I forget, there is, of course, a huge physics literature about those pneumatic colloids. I won't be citing any of them because I would probably forget some, so I just chose not to do anything about it, but probably people in the room also have worked on this, and yeah, so sorry about that. And one popular theory that you find in the physics literature is that these interactions, you can actually use an electrostatic analogy to understand them, which means that you see something like that as an electric charge that, a charge thing, a charge point particle, which maybe carries a dipole, in that case, or a quadrupole. And what this means is that if you are using this electrostatic analogy, effectively you're linearizing the problem, right? Then the charge, you can superpose them, the thing becomes very linear. And it means that to understand the whole thing, you really just need to understand what happens around one of them, right? Because then you can superpose everything. And so where did the nonlinear stuff go? Well, it's all hidden around what happens in one particle, right? And this is where the analysis gets tricky, because of course the nonlinear stuff is much harder to understand. And in these physics papers where they they use this electrostatic analogy and derive it. Actually, the only thing you can do is use a kind of ansatz to say, okay, this is how I will describe the nonlinear effect. I mean, I think roughly, I have an ansatz that looks a bit like this picture, and let's just say this is going to be describing well this nonlinear effect. I mean, from what I understood, maybe you'll tell me I'm wrong, and I would be happy to hear about it. So anyway, again, this is why it's important to understand what happens around one thing, and this is the actual nonlinear problem. Of course, the linearization problem is also something very interesting that we are actually also working on, and we hope we'll understand one day. But anyway, so I'll be concentrating on the effect of one particle, and in a very simplified situation where I assume that the particle is a sphere, is spherical, and so the domain where the nematic is just an exterior domain, like the whole space deprived of the particle. This ball, I call it B, is just of radius 1, so I have rescaled it. So if you want, all the lengths in my problem are hidden in my Xi, in my length scale there that I non-dimensionalized. I'm assuming normal anchoring at the boundary. So this is just this radial vector here at the boundary, roughly as in the pictures there. And away from the particle, I'm assuming I am like just uniformly aligned along a direction that is, as on the pictures, vertical, which I will be more precise about this later, but for now, just think, yeah, at infinity, it's roughly vertical alignment. And so, as I said, you want to understand, I mean, when one of those two configurations happens, and within that electrostatic analogy, they are usually referred to as the quadrupole versus dipole configuration. So this would be the dipole, this would be the quadrupole, and what really distinguishes them from the point of view of symmetries is that this quadrupole symmetry has an additional symmetry. It's more symmetric, right, because you can do a reflection with respect to this horizontal plane, and it stays the same, right? And we already did some work with Lee and Stan about what's going on here. And basically what we showed is that if you have a small particle, so remember the radius of your particle is 1, so when it's small, it means 1 is much smaller than the other length scale there was in my non-dimensionalized unit thing. There you actually see this. The minimizer of the energy is this. And if you have a large particle, then you should see this. Okay. The reason why you see this in the regime of the large particle, which amounts to sending C to 0, is because you end up with a harmonic map problem. And I think many people, and among them John Ball yesterday, told us that for the harmonic map problem, line defects actually have infinite energy. So that's why you don't see them, right? But in fact, when there should be also, you should be able to observe ring defects around large particles. From what I understood, they are observed in experiments. They seem to be kind of numerically stable, so there should be at least a local minimizer looking like a ring defect, even when you are in that regime here. And so this is what I want to speak about today. Actually, this is how can you find a local minimizer, say, or something like that, something that would be a metastable ring defect configuration around a large particle. Of course, you know it's not going to be a minimizer, but maybe it's still something you can observe, and in fact, it seems that you do observe it. This is going to be the setting. So we are going to be considering minimizers of the energy among configurations with normal anchoring, so as I said before, this far-field alignment condition that now I made more precise. So Q has to be close to this vertical alignment condition at infinity, and I enforce this in some integral sense because this is the thing that allows to use classical tools from calculus of variation. So don't worry too much about this. This is just enforcing in a mild way the condition that you want to be aligned at infinity. And now I'm going to be looking for configurations which are forced to have the symmetry of the ring defect. That way, I mean, I'm pretty sure I will see it, right? So which means I'm enforcing this rotational symmetry around the vertical axis and also this mirror symmetry here. And under those assumptions, then we can actually prove that what we see, this minimizer with this symmetry conditions, is actually corresponds to that picture. And explicitly, what do we obtain? We obtain an asymptotic expansion of the energy, which corresponds to a defect ring, which would be at distance 1 over absolute value of log C of this particle here. So this is the distance here. So it goes to 0 as xi to 0, as you would expect it to. And we actually have like the scale at which it does that. And you have this convergence of QXi towards some n star, as we had before, because we are sending C to 0, right? And it's really what you expect. That is the only defect that you see in the limit is just this ring defect that, because you sent C to 0, now is just the equator on the ball, right? And everywhere else, this is smooth. So this is really this picture here, right? And we also have this additional symmetry here. So what does it mean? It means that just n star stays in the azimuthal plane, so that this picture is right. So I told you, here I draw lines which are in the plane of the board, and then you imagine that you're rotating them. So really, like this picture really has this symmetry, which I've not been very explicit about what I mean by rotational symmetry here, but we were not enforcing it before, so we get it as an additional thing, right? So it's telling you that, yeah, this is really like the picture you get. But here, not considering, and that's just an actual minimizer or something. So let me emphasize that the fact that really this thing is smooth away from the equator is actually the hardest part of our work, although it seems kind of obvious for, like, I guess from physical intuition, because obviously you don't have to have more defects that would not help you with the topology, the topological constraint. But in fact, this is a subtle issue, and well, I hope I will be able to convey some of the difficulties related to that. But for now, let me just say one obvious thing is that point defects. So obviously this, okay, with these boundary conditions, you created a topological charge. You have to compensate it with some defect, right? And this does the job. It does, so now topologically you have something that makes sense. But you could always add defects everywhere and with negative and positive charge, and if they compensate, I mean, this also makes sense. Of course, you could tell me, I mean, this is stupid, why would you do that? Obviously, it will cost you a lot of energy if you do that. Well, it's not that obvious. Well, first of all, obviously, point defects, they have energy much, much lower than these line defects. You actually don't really see the effect of adding point defects when you do this energy asymptotics here. So it's telling you that, okay, you have to go to the next order, you have to do something much more subtle. But it's actually more than that. The idea that it's always better to have the least number of defects dictated by topology, we know it is false. Okay, there is an example by Hart and Lin from the 80s, where they actually show a configuration, so they are in a finite domain inside a ball, where you have a boundary condition that has no topology, so you could find an extension that would have no defect, but still, energetically, it is favorable to actually create defects. The minimizer does have defects. So it's telling you that this thing, that's what I mean by this sentence. Topology and energy minimization, they do not always agree. So this is also, even if you didn't have that issue of you have an infinite energy, this is another reason why it's hard to rule out point defects, because it's not just a topological thing, it's also like a subtle energy minimization thing. All right, so what I want to do next is actually give you some ideas of the proof of that result. So I'm going to get a bit more technical now. So let us say exactly what those symmetry constraints give us on the shape of our solution. So I will be using cylindrical coordinates, right? Rho is this distance to the vertical axis, phi is this azimuthal angle, and z the height. And the rotational symmetry is basically just asking that you start from something in that plane here, in that half plane, and you rotate it by angle phi, okay, with the natural rotation. And you're also enforcing the mirror symmetry, so you're saying that when you're here, you can know what happens here by just doing this reflection, okay, and the reflection I call S. So that means that at the end, I will be effectively walking in this 2D quarter of a plane minus a bit of this ball here, right? And when I plug that symmetry constraint into the energy, at the end, effectively what I'm going to be working with is a 2D energy, right? I mean, phi goes away, and so you really have a 2D model where you still have this gradient Q squared, you still have your potential, and you just have another term here that comes from the phi derivatives in the gradient, but really you won't have, we won't be worrying about it much, so we can just forget about it. And what's important to understand is that it also comes, because you're doing this change of variable, it also comes with this weight rho here, right? So, okay, it's a 2D energy, but when you're near the axis, you have a weight that degenerates, so it's not really like the 2D model of Lambda de Gennes, and also you're in infinite domain that can create issues. All right, so let's try and understand more about the energy asymptotics, and the easiest part is the upper bound. This is actually constructing an ansatz, and you hope it gives you the optimal energy. So here I'm just recalling the energy. I'm in that domain D, that 2D domain D, and from the pictures, I know that I want everything to happen in that small region here, right? So this is where I'm going, this is where it's important to explain the construction, right? And what do? You have to put a defect because there is topology, but, and also because there is this weight, you want it to be as close as possible to the equator, right? Because otherwise it costs more when you go away. So what you do is, of course, you cannot just glue it. You can just put it here because you have strong anchoring conditions, so they pull your defect away. So what you do is, so these pictures, again, when I draw those lines, you have to think it's the director, right? So around the defect, you have to do something like with the actual Q, relax the unit constraint, but you understand pretty much what's going on with just that. And so you include this degree, I guess it's -1/2 defect, and you put it at first, you put it at distance sigma from the equator. Okay, why not? You can do a construction like that. And what do you see? What does it cost? So this P log of 1/sigma, this is the cost so effectively, what are you doing? You're going from this to this here, which is almost horizontal, and you have like to rotate the face, right? But since I'm doing it here on this larger circle here, I'm actually effectively looking at a boundary vortex. So I have just half the space to do my rotation. So it costs more. So that's why here I have a P log 1/sigma, which is to be compared with this P/2 here, which comes from the actual defect I put here, but I have to consider a smaller length scale. And there I am allowed to rotate, to use the full space to do the rotation, so that's why it costs a bit less, right? And for people who do Ginzburg-Landau, it's classical that boundary vortices, they cost twice interior vortices. And here, you want the vortex to go to the boundary, but it's not at the boundary yet when you fix the Xi, right? So here, the cost is P, but then you have P/2 when you are really at this length scale here. And, but since you are away from the equator, you have this additional cost, right? You have to multiply by the weight. And then you optimize with respect to sigma, and this is where you see this optimal distance coming in, right? you choose the best sigma possible. So this is just a 1D calculus, right? You differentiate this thing, and you realize that the optimal sigma is this 1 over the absolute value of log C. Okay, so then you obtain this lower bound, and so you see the main order is just pi over 2 log 1 over C. So it's exactly the cost of an interior 1/2 defect. But because you're actually not allowed to, because you actually, if you put it in the interior, you have a weight and you have to play with that distance, you actually get something else here. So it's not the usual log 1 over epsilon or log 1 over C. You have this other term that kind of breaks the scaling invariance of this thing, right? And then you have a large O of 1, and we won't go further than this expansion. Okay, so this is the upper bound. This is how it comes up. And so this was just a construction, and of course what you want to do is find a matching lower bound. So what's the rough idea? Well, first, because of the mirror symmetry, what does it do for you? If you think just of director, on this line, if you have mirror symmetry, on this line you have to be invariant under your symmetry, right? So it means the director, it has to be invariant by reflection with respect to the horizontal plane, so it's either in the plane or orthogonal to the plane, right? There is no other option. But here you have anchoring conditions that force you to be in the plane, like this radial thing, and at infinity, you'll be orthogonal to the plane because you have your condition at infinity. So at some point in the middle, you have to change something, right? You have to have a defect. So that's why mirror symmetry forces a defect on this rho axis, right? So something will happen here. And then the idea, as I told you before, is that the weight rho, it should push your defect towards rho equal 1, right? So that's why, again, all the analysis for the lower bound will happen in that region here. And again, you see the same picture. Basically, there's going to be one defect. So maybe it is at some distance, sigma, that has to go to 0 because of rho. And then you use standard Ginzburg-Landau tool to obtain a lower bound. In fact, I say standard Ginzburg-Landau tools, but this is actually quite technical. All the tools are out there to do this, but you have to kind of put everything together. First, there is the classical Ginzburg-Landau tools. Here I cite the BBH book. We also use the later tools of Struve, Bob Gerard, Etienne Sandier. Now we have a weight. So we also have, we have to adapt those tools, but this has been done in papers by André and Chaffrir and Beaulieu and Adigi. And in fact, it's not Ginzburg-Landau, it's Landau de Gennes, right, 2D. So we also have to adapt some tools due to that, and this has been done, for instance, in a paper by Giacomo and a paper by Dimitri and Alberto Montero. So basically, what I want to tell you is to obtain this, it's not that easy because I'm telling you, okay, I have one defect on the axis, but in fact, I don't know, there could be more. And if there are more, then it's, complications can occur. And this is why you need all these tools to rule all the other possible defects out and realize you have this lower bound. And of course, when you have this lower bound, since the sigma I chose before was the optimal one, it's larger also than the one I found before, right? So this is basically how it goes, and I'm hiding the technical details here, but basically there were already the tools out there to do that, right? So we just adapted them. It's not trivial, but it's not that hard. Now, let's talk about the issue that I said was actually the subtle one. It's understanding better the limit configuration, in particular the fact that it has no point defects. So what do we know? Just for the start on the limit configuration, where thanks to the upper bound and the lower bound, we know that as long as we stay away from that region, we have an upper bound, right? You just put the two together because the lower bound was actually obtained just in that small region, right? So when you put the two together, you realize that for each fixed delta, staying away from the equator here, you have an upper bound that depends on delta. And so for each fixed delta, you have like weak, standard tools allow you to pass to the limit in H1, right? The compactness I was referring to before, because you have bonded energy for fixed delta. So you obtain a limit, you obtain a limit configuration, and for any fixed delta, this n star here is a minimizer of the Rosen-Frank energy among all maps which are S2 valued and have our symmetries, right? And here, when I write omega delta x is the symmetrized version of this d delta x, right? The one where you apply the symmetry by mirror symmetry and also the rotation. Okay, so you obtain in the limit a configuration that is really a minimizer as long as you stay away from the equator, right? Because at the equator you have infinite energy, you cannot really say anything more precise than that thing. And I said what you want now is further properties of n star. So there were two properties. The fact that you have this additional symmetry, right? And so it stays in the azimuthal plane. And also the fact that it's smooth away from the equator. And here the equator in my coordinates is just z equals 0, rho equals 1, right, this point here. And why is it difficult? Well, first of all, I mean, how do you usually do that kind of stuff? You use comparison maps to compare energy, right? But here, n star, you know it has boundary conditions everywhere. I mean, here you don't really know. It doesn't have like explicit boundary conditions. You just know it's the limit of something, right? So in some sense, the boundary values of n star here, they are constrained in some way because you have like this bound, but they are not explicit, right? So this is gonna be always a problem when you want to build comparison maps. And the other difficulties is that, as I said before, I mean, point defects, of course, point defects away from the z-axis, there would actually not be point defects because with the rotation, then they become line defects. So these we already know they're not happening. What's hard is point defects on the z-axis. And there, remember, I mean, my energy, it had a weight rho, so really the 2D analysis is not gonna help us there because the rate vanishes on the z-axis, so you lost everything, right? So you have to do something else. And let me try and tell you how we do that. So the first idea, so let's start with that symmetry property, right? So the basic idea is quite simple. So let's write n star of rho phi and z as just something in the plane, n star of rho z, and then you rotate it by phi, right? Because it has this rotational symmetry. And now this thing becomes just show that n tilde is perpendicular to E2. And here you have to imagine that I have my E1, E3. So E2 is the vector like going perpendicular to the blackboard, right? So this is, I want to show that n tilde stays in this plane, in the plane of the board. And the reason why it should do so is actually the same reason why geodesics on the sphere, they are along great circles, right? Because you would lose energy by deviating from a great circle. And how do you see that? Well, if you project your n tilde into something that has that stays in the plane, then you actually decrease energy. Okay, but are you allowed to do that? Yes, you are allowed to do that if you are staying in your admissible space, right? And it looks like this does preserve boundary conditions because my boundary conditions, they were here, right? They were just already in the good plane, and also they had the first component was non-negative, so this is really preserving boundary conditions, except perhaps on that part where I'm not too sure about what happens, right? So this is the part that is tricky here, is understanding what happens with the boundary conditions of n tilde here, because remember, I'm only allowed to use minimality of n star away when I cut out a small piece here. And so why do you expect things not to be too bad? Well, you have to remember that you have this upper bound, right? So the energy in the exterior domain is less than this pi over 2 log delta plus something plus a constant. And now let me just rewrite pi over 2 absolute value of log delta as, in this complicated looking way, as just the integral from delta to 1 of pi over 2 over r squared r dr. Okay, and here I'm using these coordinates here that are on my picture. So r and theta are polar coordinates with respect to the point here. And so, okay, this is what it is. But on the other hand, if, so part of the energy is basically the gradient of n tilde squared, right? So part of the energy, you have the derivatives with respect to theta, which come with the 1 over r squared in front. And in fact, just from what you know about geodesics in S2, because here, this n tilde, it has to go from here to something almost horizontal. I mean, you know from geodesics in S2 that you have a lower bound on the energy, right? The energy has to be greater than something because this is just, I mean, geodesics in S2, you know them. And it happens, the lower bound happens to be pi over 2. So what happens here is that with this upper bound, it's actually showing that you have to saturate this lower bound. You have to have energy very close to the 1 over geodesic. And now you have to work a little bit. This is hidden in that small arrow here. But in fact, there is a property of stability of geodesics on S2. So if you have energy close to the minimal energy, then in fact, you must be close in some sense to the geodesic. And this is what you can use to say in some sense that in fact, the theta derivative on L tilde has to be almost constant, right? So in some sense, you know that on that part, you're actually very close to the ideal defect that you would, that the one, for instance, we used as a construction map to get the upper bound, right? And you get this closeness in an H1 sense, because this is the natural thing to do when you have minimizers of that energy. And this is basically enough to construct some kind of layer here so that you don't actually mess with the boundary conditions here when you want to use that comparison map. So I'm hiding a lot of like quite painful technical details here under the carpet, but really like the main reason why it works is this thing here, just saturating this constraint, right? I do have 3 more minutes, right? 4, great. Okay, so this is how you manage to get this additional symmetry, and now you want to do the other stuff, which is ruling out point defects on the z-axis. Now, point defects on the z-axis, what do? On the z-axis, because of the rotational symmetry, you basically have to be always vertical, but you could be vertical pointing up or pointing down. Okay? Oh, by the way, maybe I should say something. In principle, n was not oriented, but I can choose to orient it. And here, so I'm orienting it here. But since I don't know exactly what I'm doing here, I don't know if here I should orient it pointing up or down. I mean, this is not so clear, okay? But anyway, so on the z-axis, so defects, they happen when you change direction, okay, from up to down, down to up. And if you have just an even number of those point defects, then I can say I can orient things here too, okay? And I have an even number, so this is like in this picture here, and now I'm actually pointing up. So this looks to be like the better case because it's actually the case that corresponds to a defect of, that should correspond to a defect of degree -1/2 here, which is the one we used in the construction, right? So this should be the case that will be the relevant one. And now the idea, as I said, I mean, it's very hard to use just energy comparison to understand that you have no point defects. So instead, we use the trick that we actually used already in a much simpler setting with Stan and Leah some years ago, which is to look at the set where you're pointing rather down than up. That means the set where the third component of my vector is negative, right? And if you can say that this set stays away from the boundary, then in fact, you can just, inside it, you can just reflect it, and it happens not to change the energy. And it means that actually the configuration where it was not pointing down, but it was pointing up has the same energy. But since you have analyticity given by the equation, you can rule out that because you don't want to be, I mean, analyticity, if you have an analytic map, you should not be able to do that kind of reflection, right? And so that way you can rule out that kind of connected components, and what it means is that this was actually not happening, right? Okay, but this relies very much on the kind of estimates I showed you before, that you can say something about what's going on here, except here you have to be a bit more careful, because see, this would not just follow from H1 bounds. I mean, you would need probably L infinity bounds, and this is just borderline, so you have to be a bit careful here. But anyway, you can show that. I mean, just building on the ideas that were on the previous slide. Okay, this is nice, but now if you still have to rule out an odd number of defects. And basically you have to rule out, I mean, the worst case is if you had just one defect, which topologically is admissible. You could have like this plus 1/2, I guess, -1, -1, and this will compensate with the, I mean, anyway, it makes sense topologically to have this, even though it should be energetically non-favorable. So what happens if you have an odd number of point defects where I didn't do the picture, but you will actually be pointing down here? So obviously, this will never happen, right? Because you will be pointing down somewhere at this boundary here, right? So you cannot use the same thing. But still, using the same kind of ideas, just refining them, you can show that you will have at most one point defect. And again, this relies on improving, again, the estimates there and doing much finer stuff. And then this is what I won't have time to tell you about, is now the really like hardest part that took us a long time to understand, is to rule out that last possible point defect, because then all of this kind of fails. And you really have to, here I was always arguing in the level of the limit, right? And if you want to rule out the point defect, or maybe we were just stupid and couldn't do it, but what we did was that we had to come back to the actual Xi positive configuration and to do much finer estimate on the QXi and to rule out also that case, but I don't have time to explain you that, so I'll stop here. Thank you.
I think we have time for one quick question.
So, excuse me. So you ultimately, what kind of stability do you think is true about this guy?
So I have no proof of anything, but Dimitri did numerics, and it looks like this guy is, I think it agrees with numerics done in the physics literature and with experiments. It looks like this guy should be stable. So you would think that maybe you could like move a bit the ring and then it would be smaller, and so it would be better energetically, but apparently from numerics it is stable. So I'm not sure what happens there, but
so I mean, just speculation here. Do you think is there some underlying renormalized energy that where some limit of this is a minimizer of some limiting energy?
So my guess is there should be a renormalized energy, but in fact, there is one point that makes it hard to obtain a renormalized energy. I mean, there are many points. First, you don't know how to do the analysis, right? But let me point at something more concrete. When you look at this infinite cost, you know, in the usual like Ginzburg-Landau thing, this is something, you just have this type of things, and this is something that has a nice behavior with respect to rescaling, right? You replace 1/Xi by R/Xi, and the log R goes away. Of course, when you look at this infinite cost here, you don't have that property anymore. And if you look at the proof of all the renormalized energy stuff, I mean, it relies quite a lot on that kind of properties. So it's really not that clear how to get a renormalized energy here. So I hope there is one, and maybe we can get it someday, but really I don't have a proof and I don't know how to do it.